Hi, welcome. I'm Tony, the voice behind Talking Hands Math, and I'm so excited that you considered this video, this introduction to this large project I have about teaching precalculus. And as I probably said in the introduction to this series, I thought precalculus is a wonderful place to start. It really wraps up all these high school topics such as functions and graphing and trigonometric ratios and exponents, logarithms, so many different topics, matrices, and it really gets you ready for what is, I think, the beginning of math is calculus. And in order to do well in calculus, you got to have a firm grasp of precalculus. So that's what this whole series is about. I'm taking this text, and the text is this one, Precalculus with Unit Circle Trigonometry by David Cohen. It's the fourth edition. If you'd like a copy of this book, I'll have a link in the description. And I don't plan on being in front of the camera all that often because I don't really think I'm all that interesting. But the content is, and what I really want the viewer to take from this is I want this to be a comprehensive course, and it'll be lengthy. I will go into bobs and weaves of content, and I will give you as complete of a picture as I possibly can to get the student ready to succeed in calculus and even beyond that. So, what I want you to do is, I don't want you to simply watch the video. I want you to get a copy of the text. I want you to have the text in front of you as I'm going through. I found a PDF version of the text that I'm going to be doing on screen, so everything's real nice and clean. But I want you to follow through with the text, and I want you to get a notebook, maybe one of those journal books, and keep a running journal of notes of the things that are important. And then further, what I really would love for you to do is I'd love for you to take photos of your notes and email them to me. I'll have a link to my email in the description. And I want you to email me uh, images of your journey as you're working through this because we're all going to be in different spots. It's 2023 right now, and you'll be in some place. Maybe you're following along as I'm publishing these videos, but maybe it will be 10 years from now, and I want to collect those notes that you have. I want to collect the work that you've done from this textbook, and I want to display them. And I don't know exactly what that's going to look like. Maybe I'll have a website or something, and I'll just collect all the images. And uh, I don't know. I really want this to be a community. I want us to share. I also plan to have um, live streams of this content. We can dive deeper. I won't regurgitate what's already on my video lessons. I'll just dive deeper and we'll explore these things. And maybe you've worked through ideas and you have further questions related to these certain topics. And then from there, oh man, I'd love to move on to calculus and linear algebra and differential equations and all these wonderful topics. So, oh man, this is super exciting. I'm pumped. And we're going to be talking about uh, sets of numbers to begin with. So, let's go. Okay, so in chapter one, they call it fundamentals because these are important ideas. We use these ideas, they're so fundamental that they're just interwoven with nearly every concept that goes on in the book. So we start in with what are numbers? And you can't just say a number's a number. We have different types of numbers, and we have what are called the real numbers, and they can be expressed in decimal form. We have 7, that could be 7.0000. We have the square root of 2, which is approximately this 1.4. It's actually an irrational number. It's a number that it's in decimal form, but it never ends and it has no patterns to it. It's really crazy. And then we have these right here, these negative 2/3, that could be negative 0.6666666, and that's a real, these are all real numbers, but they're also rational numbers, and I'll explain those differences in a moment. So that bar notation, that means that the 6 repeats, okay, so on. And we can talk about all these numbers exist on a number line, and the number 0 is referred to as the origin. And oh, this gets talked about in calculus quite a bit. Um, the idea of a one-to-one correspondence. So the fundamental fact is that there's a one-to-one correspondence between the set of real numbers and the set of points on the line. So what that means is that we have and I'll bring this in a little bit tighter here, a one-to-one correspondence. So uh, every point on this line has a real number that's assigned to it. One-to-one correspondence. One dot on the line is one number assigned to exactly that dot. And we have a sprinkling of those right here, but we can have decimals in between and so on. And then there was another note up here I wanted to mention, because I'm going to dive into everything in here, into this text. This is not just a general review. I'm going deep. And we have our natural numbers. This is another type of number we have. They're used, so they're saying here, it's been used since, fractions were employed as ancient Egyptians. I mean, we're talking, these are old numbers. But actually not that old. I mean, the stuff that we're talking about in this book, some of the stuff in this book is only a couple hundred years old. And when we're talking about ancient Egyptians, only 1700 BC. Good golly, that is not that long ago. Uh, in ancient Greece, 400 BC, we had numbers like the square root of 2, which cannot be fractions. That's an irrational number. I'll talk about that in a moment. Ooh, here's a question. What secrets lie hidden in decimals? Huh. A number for your thoughts. Nice. I'm going to have to check that out. Okay. So, we have the sets of real numbers. And we have natural numbers. So, we have the set of natural numbers, and I think these are important to include in notes here. So we have natural numbers, integers, rational numbers, irrational numbers. And for this, I usually like to have a graphic for this. And there's graphics all over the internet. In fact, if I were to start a browser here and I did, what was it? Real numbers. So I'll show on the keyboard here. Real numbers. We will have graphics. And right here, you can see I'm about to duplicate this right here. We have all these kinds of graphics of what are real numbers. And I'm trying to, so I will talk about this. But and so to talk about these different numbers, we have what are called, like I've said, the real numbers. Real numbers. And the real numbers are made up of two main types of numbers. We have the rational and the irrational. And boom. The rational numbers. Those are fractions. Essentially, they are fractions of integers. I'm going to write a little bit neater because that didn't work out so well. Fractions of integers. So, when we're talking about fraction of integers, we need to know what integers are. So, I will then have a box inside of here, and I'm going to call these integers. Oops, integers. And an integer, they are just positive and negative whole numbers. Well, what's a whole number? And so inside of there, whole numbers, Whole numbers are natural numbers, including 0. What are natural numbers? And so we can talk about natural numbers. Natural numbers are really just our regular counting numbers. That's like 1 and 2 and 8 and 2000 and so on. The whole numbers include all those natural numbers, but you also have 0. Okay, so now I've in this diagram, I've quickly, and this was so cool about math, is you can so succinctly say, hey, here's the natural numbers: 1, 2, 8, 8,000, 2,000,000, any kind of positive counting number. And counting number, like I have 1 apple, 2 apples, 3 apples. And then all of this, you include 0, and now you've talked about the entire universe of whole numbers. Integers, they are the positive and negative whole numbers. Or we could also say that they're also said to be the whole numbers, including I'm sorry, the whole numbers and their opposites. So maybe integers, I will say, are whole numbers and their opposites. So now we can leverage all this stuff here. Fine. These are all integers. But then if we took the opposite of any of our natural numbers, or any of our whole numbers, I could say, we could say an example would be -2, or -8, or negative 212. All of these are the integers. So when we get to the talk about rational numbers, they are fractions of integers. So we take our any two integers we want. An integer could be like, 1 is an integer and 2 is an integer. And there's a rational number. It's a fraction of integers. But you can't have 0 as a denominator because you're not allowed to divide by 0. And more on that probably in another lecture. But if I take any other two integers like -18 and 361, there's a rational number. And I want to then talk about, well, in the description of rational numbers, ratio, they say here that the rational numbers are ratios of two integers. It can be proved that a real number is rational if and only if the decimal expansion terminates or repeats. And so that is the behavior of rational numbers. They either terminate, they come to an ending, or they repeat. And that's what happens here. So 1/2 is that's a terminating decimal, 0.5. I don't know what -18 over 361 is, but I do know what, I don't know, like 1/3. I can make it easy. 1/3, that's a rational number. 1 is an integer, 3 is an integer, and the ratio of integers, or a fraction of integers, is a rational number. And this is 0.3, and the 3 repeats. And so I think of rational numbers as we know what's going to happen. When it's rational, we know that this is going to end, or we know what the next number is going to be. And that's essentially rational numbers. Irrational numbers. Well, you cannot make that can you cannot express as a fraction of integers. So the classic examples are pi. Pi is this decimal that is about 3.14159265358979323 and so on. And the three dots mean they just keep on going. But the it doesn't end, but it also doesn't have any repeated patterns in it either. Another one, a classic one. Another classic one is the square root of 2. What times itself is 2? And you're probably thinking, well, 1. But no, 1 plus 1 is 2. To actually figure that out, that is about, let's see, that is about 1.14, I think. And this one, the decimals keep on going too, and there's no pattern to that decimals. There's another very popular one called E. That's actually a number. And that's about 2.7 whatever it is after that. And so we cannot express these as fractions of integers. Their behavior is a decimal that never ends and has no patterns to it. So together they make the real numbers, the real number system. And then there are non-real numbers, which are imaginary numbers. And we'll have lectures on that another time. So to continue with, I've talked about all these things, and it's important to have notes on these. Ooh, and here's a little tidbit here. So the irrational numbers, they're real numbers that are not rational. Okay. In section A3, so the appendix, in the appendix in the back, there's a proof that shows that the square root of 2 is irrational. Maybe I'll talk about that another lecture. The proof that pi is irrational is, it's more difficult. The first one to prove that it is irrational was a Swiss mathematician, J.H. Lambert. And check this out. 1728. We're in 2023 right now. This is only a couple hundred years that we knew for a fact that it was irrational, that it was proven. Now, they probably had an idea that it was irrational, but they didn't really know it and prove it until this time, the 1700s. This is not old stuff. This is new. So, usually, let's see, right here. So we have the square root of 2 is approximately there on the number line, and it has a spot. And so they say here, it's convenient to use number lines to show the reference points. Perfect. And later, we're going to have number lines that have not only a horizontal axis, but a vertical axis as well. And we'll be using, when we're talking about trigonometric ratios and the graphs of them, we often use pi as our x-axis. And we will know that 1 is somewhere around a third of the distance to there and so on. So having number lines like this, we need to be familiar with as well. And we then dive into our basic relations for numbers. We have the less than or greater than, and these, when I was in elementary school, we call them the alligator signs, and this is an inequality. So these things are called inequalities. They're not equalities. They're a comparison of one number to the other, and and you've probably seen these here, and we're going to be talking about intervals soon, and any number. So any uninterrupted portion of the number line is referred to as an interval. Oh boy, these turn out big in calculus. And we see notations like this: a is less than x is less than b. That means that both the equalities a is less than x and x is less than b are holding there. So we can also say that x is in between a and b. So we have our open intervals, which are consisted of these parentheses here, and that's all the numbers that are in between a and b. So, but it does not include a or b. And the closed interval, denoted by these brackets here, are the numbers that are in between a and b that include a and b. Okay, and so they say, see this figure here, and we see that here it's in between a and b, but it does not include a and it does not include b. And here it's in between a and b, and it does include a and it does include b. And sometimes we have one parenthesis here and a bracket on the other side, as we'll soon see. So I don't know if this is worth writing down in your notes, but if you are not super tight on this, write it down. Our notation, a is less than b, okay, yes, and 2 is smaller than 3. Negative 4 is smaller than 1. These are a couple of examples of that. This is a is less than or equal to b. Okay, so 2 is smaller than 3, or it could be equal. And this is also a true statement. 3 is less than or equal to 3. We can also write the flip side of this. In fact, this right here is exactly the same statement as this. They mean the same thing. It's just switched around. B is greater than A. Okay, and we have these statements here that say a similar thing to this. And then this right here is the exact same statement as this. It's just flipped around. And for this here, we have brackets that indicate these and parentheses. So like we said here, this statement, A is less than or equal to X is less than B, can also be written like this. This and this mean the same thing. And wait, I'm sorry. No, this. This right here can be written like this. And this right here can be written like this. And I see the parenthesis here and that inequality and that bracket and that other inequality with the extra line right there. So those two things mean the same thing. And so this right here is an interval notation. And so we're going to try to understand that interval notation. So we can go back and forth from this interval to the different notations here. So show the interval on a number line. Okay, so we have bracket, bracket, and we have bracket, bracket. Okay, parentheses, parentheses. Okay, and we have these inequality statements that mean the exact same thing. So it's really, there's nothing really to calculate here. It's just noting that this and this mean the exact same thing. And when you see these, you would expect to see this on a graph. So this is 3 representations of the exact same information. Notice here, parentheses, no, strictly less than, bracket, less than or equal to, and X is in between. So this means the numbers in between -1 and 2, but also could include -1. And so we have our unbounded intervals. So that really, I mean, it sounds scary, but look at this. They're intervals that extend indefinitely in one direction. So they're not bounded. If it was bounded, we would have something right here, and there's the bound, but that's not the case. So it really just goes forever in one direction. And the notation for this, for this graph right here is this. 2 does not include 2, but it starts at 2 and it goes to infinity, to positive infinity. So it goes forever to the right direction. And here we have a moment of caution where they say the symbol, that's the infinity symbol. It's not even a number. It's really just indicates the interval has no right-hand boundary. In the box that follows, we define several types of unbounded intervals. Note the last one, negative infinity to positive infinity, actually is the entire real number line. So that means everything. And here we go. So if you're not savvy to this notation, or this feels newish to you, or you knew it one time and you forgot about it, it's worth writing down. So we have our notation. So here, it's not, I view it as this is not touching anything. It's starting at A and it's going to positive infinity, so this is unbounded. Okay, boom. Here, it is touching the A and it's going to infinity. So it is including the 2 and it goes forever. And by the way, also, all the numbers, so this is 3 different ways of saying the exact same thing. Our notation, the inequality that means the same thing, and the graph. So if I jump down to here, it's, and by the way, whenever you're dealing with infinity, you're never going to have a bracket. It's always going to be parentheses, because the infinity, negative infinity or positive infinity, it's not a number that you can actually attain. It's this concept that you're really just kind of going in that direction. So you'll always have a parentheses when you're dealing with infinity. And so going from negative infinity up to the number A, that's the same thing as all the numbers less than or equal to A, and this is the graph of all the numbers less than or equal to 2. And then, like I said, that's all the numbers right there. So we're using notation for those. So here's a few examples. And right there. Okay. So we have in our examples going from negative infinity to 4. Okay, there we go. Not too hard. Going from -3, but not starting at -3, but not including -3, and going to the positive. So yeah, that shouldn't be too bad. And by the way, I took a photo, since I have the book right here, of A2, which is kind of weird. This is section 2 of the appendix, which is on page A5. Kind of confusing, but here is what they're talking about: some of the fundamental properties of real numbers. And I don't know if you've seen these, likely the commutative properties of addition and associative properties and zero property, the fact that you could, if you add 0, it's the same number. If you multiply by 1, it's the same number. The opposite, additive inverses add up to 0. Multiplicative inverses multiply to 1, and the distributive property, and so on. You should be familiar with those. And then we have this theorem: let A and B be real numbers, then this is basically all the properties up here. If you multiply by 0, it's 0. Negative A is -1 times A. The opposite of negative A is A. A times negative B is negative AB, and negative times negative is positive. And so these are the basic ideas. All right, back to the lecture. So what we have here is the exercise set. And when we get to the exercise sets, I'm really just going to do a sprinkling of these. And if you want me to do some more, I'll make more videos of it. But I thought I'd just kind of touch on 4 or 5. I mean, there's so many. There's got to be thousands of questions in this book, and there's no way I can get to all of them. But we can hit a sprinkling of them. For instance, maybe one from this set here. So determine whether the number is a natural number or whatever it is. The following facts will help you in some cases. So I would say, if I come back to this here, I'm just going to throw it in here. What? This is a whole number? No, it's not. It's an integer. What am I doing? It's an integer. This is a rational number. B is a rational number because it's a fraction of integers. And this is also a rational number. And by the way, what I should say is this is the lineage. Natural. I got to write this a little bit neater here. I'll just have it. I'll pause and have it written. All right, I'll probably include these in the notes, but this is the lineage. If you can identify what kind of number you have, like here, if I identify this as an integer, then that means if it's an integer, that means it also qualifies as a rational number and a real number. Here, rational. If I identify, boom, it's a rational number, then it also is a real number. The square root of this, I don't know what the square root of 27 is. I know what the square root of 4 is. That's 2. Because this can be the same as the square root of 27 over the square root of 4. And we know the square root of 4 is 2. But I don't know what the square root of 27 is. And so this is going to be irrational. So that one's irrational. And if it's irrational, it's also real. But it's none of the other stuff, too. So I would say this is irrational. Oopsie. Okay. This right here, this is, wow, 10 to the 6th power. That's a 1 with 1, 2, 3, 4, 5, 6 zeros over 1. That's definitely rational. Oh, you know what? Yeah, it's rational. However, I could go back farther because this is a natural number, right? So if I say it's natural, then I've now said that it's not only is it natural, but I've also said it's a whole number. By saying it's natural, that qualifies it as a whole number and an integer and a rational number and a real number. So there's that. And then this one here, this is 10 to the 6. And I think I'm going to do this. 10 times 10 times 10 times 10 times 10 times 10. That's 10. That's what 10 to the 6 really means. 10 times 10 times, and I have more ideas about that too, but I won't get into that. And then 10 to the 7th is 1, 2, 3, 4, 5, 6, 7. And okay. And what we can do is we can cancel these all out. And this is the same as 1 over 10. And 1/10 is, that's rational. That's a rational number. Do not confuse. 1/10 is not the same thing as 10 over 1. And if you think about this for just a moment, this is how many 10s fit into 1. Well, not many 10s fit into 1. Just a part of a 10 fits into 1. And this is asking how many 1s fit into 10. And there's 10 of them. So if you make these decimals, this is 10.0 and this is 0.1. I mean, put that in your calculator and you'll see. So they're very different. And so I would say that this is rational. Okay. Let's throw a couple more out here. Let's dive into express each interval using the inequality notation. Okay, so I can show the given interval on the number line. Okay, so I'll have to do a few of them over here. So the inequality would be x is in between 2 and 5. So 2 is less than x is less than 5. That's the inequality. And the number line would have to be 0's here, 2 is here, 5 is here. And we'd have to go parentheses, parentheses, and everything in between. There's number 41. And I'll go, I don't know. When I look at number 44, I always think of cheating. So we're looking at -3 halves is less than or equal to, because we have the bracket, x, which is less than or equal to, because we have a bracket again, 1/2. Oops. About to put a bracket. Now, if I have a number line, I cheat, I said, because I will put 0 here, and I know -3 halves is to the left, and I know +1/2 is to the right, and I'll just put a bracket here and a bracket here, and it's everything that's in between. I'm not going to scale it out and go by halves and whatever. I mean, I could, but I didn't feel like it. Let's look at number 53. For number 53, I have, what is this? So it's unbounded. So we're looking at pi. Pi is definitely an important number. And x, and we're looking at all the numbers smaller than pi. So it's less than pi. That's what this is saying. All the numbers less than pi, because it's going negative infinity. If this were positive infinity, then we'd be we talk about numbers bigger than pi. I pause because if we want to talk about the numbers bigger than pi, then we would do this. And we would go boom and here. And I pause for a moment because I'm thinking, wait a minute, could you actually, yeah, pi's actually have value, even though it's irrational and it has a decimal that never ends. It has an exact spot on the number line. So a bracket would be okay. So here we have that, and then our number line. Again, I'm going to cheat. Pi is somewhere to the right, and I'm going to go like this, parentheses, and that direction right there. And there you go. Okay, this is going swimmingly. And by the way, if you have issues with any of these, like you want, I'm jumping around here, but if you want me to dive into something else, I'll dive into it. You just let me know. I think that this exhausts what we have. Okay, so I'd like to jump to the most challenging. Usually, section C is the most challenging part, and I'm going to give myself some room here. And we're asked to give an example of irrational numbers A and B such that the indicated expression is rational and irrational. So we need to, what this is saying is we need to add two irrational numbers so their sum is rational. That sounds tough. Like, um, and and it doesn't say that A and B have to be different numbers. It just says that they're two numbers. So the only way I can think of making 56, for number 56, I'm trying to make them rational. So if A were the square root of 3, that's irrational, and B is also the square root of 3, I'm sorry, the opposite. Oh, there we go. There we go. Now they're two different numbers. Yes, that's it. They're two different numbers. One is the square root of 3, and the other one is the opposite of the square root of 3. So they are on two different parts. See, they're two different numbers if they exist in two different places on the number line. 0 is here, the square root of 3 is to the right of it, and the opposite of the square root of 3 is to the left of it. They're in two different spots on the number line. Thus, they are two different values. So, if I add these together, the square root of 3 plus, and I'll put this in parentheses, the opposite of the square root of 3, that's A plus B, they equal 0, and 0 is rational. 0 is rational because 0 can be expressed as a ratio of two integers. 0 is an integer, back to the lecture. And, pick the number, 8, whatever, it doesn't matter. 0 divided by 8 is 0, so 0 is definitely rational. So that takes care of part A. Part B is we need an A and a B to make them, so A, let's call A, again, the square root of 3 is irrational. And B would be the square root of 5. Because I don't, and notice, I skipped the square root of 4 because the square root of 4 is 2, and that is rational. Okay, so I skipped that one right there. And so if I add these two together, the square root of 3 plus the square root of 5, that's going to be irrational. Okay, so I made a case where they're rational. When you add two rational numbers, it's rational, and when you add them, they become irrational. Let's go with 57. I'll go with 57, 58. So there's 56. I'm going to erase all this stuff, and I'm going to make this bigger. And I'm now going to go to number 57. We have to get a rational example and an irrational example. So 57. Part A, making these irrational. So A and B. I need to be able to multiply them so it's rational. So let's go with the square root of 2 and the square root of 8. So what you might know is if I take A times B, that is the square root of 2 times the square root of 8, which is the same thing as the square root of 2 times 8, which is the same thing as the square root of 16, because 2 times 8 is 16. And then now the square root of 16 is 4, which is rational. So here's an example. A would have to be square root of 2, B, and this is just one example. There are so many others that I can come up with. 2 times 8, I mean, there you go. Because they're asking for, make them rational. Boom. And then if we go for B, the irrational, this will be just too easy. A would be the square root of 2, which is irrational. And B would be this equal to the square root of 10. And there you go, because a times b would be the square root of 2 times the square root of 10, which is the square root of 2 times 10, which is the square root of 20. And I have no idea what the square root of 20 is. I mean, it begs to be 10, doesn't it? But we're not talking about half of it. We're talking about what times itself is 20, and there you go. So I answered that one there. And let's go on to 58. I'll erase all this and do 58, and we need a divided by b. So let's see. That one shouldn't be so hard. I could do so for number 58. If I make a divided by b, so let's go with an irrational number like okay. How I mean, this may look like cheating, but I mean, they didn't say I couldn't cheat. What if a were the square root of 32? I don't know what the square root of 32 is. I know what the square root of 36 is. 6 times 6 is 36, but the square root of 32, don't know. It's going to be some weird decimal. I mean, try it in a calculator. You're going to get this wild decimal. And b could be the square root of 2. So when you have a divided by b, that's the square root of 32 divided by the square root of 2, which is the same thing as this big square root of 32 divided by 2. And here we go. 32 divided by 2 is 16, which is 4, and it's rational. 4 is rational. And then, so this is the A portion. And then the B portion, let's call A to be the square. I mean, this is way too easy. 12. And B to be the square root of 2. And so if you have a over b, that's the square root of 12 divided by the square root of 2, which is the big square root of 12 divided by 2, which is the square root of 6, which is irrational. And so there you go. There's examples of both. And so that concludes this lecture. And a few examples I did from here. And let me see your notes. Send me an email. My email is tonyzerrer@gmail.com. Send me your notes. Send me photos of your notes and the work that you did, and ask me questions, and I'll make another video. Maybe we'll have a live stream about your questions. I would love that. I appreciate you watching, engaging, and learning. And I hope that you've found this fun. I know I did. And we'll move on to the next lecture. Till then, bye.